All right, folks, it is 10:30, and we've got 7 speakers to fit into 55 minutes, so I'm going to go ahead and get started. My name is Cliff Snyder. I am an SRE at LinkedIn. I've been at LinkedIn for about 2.5 years, and I'm here to talk to you today about the ngraph of the week. So what is an ngraph? Ngraphs is our internal metrics visualization tool. There's an API on the back end called Autometrics where you can fetch all this data about a service or a particular metric you're interested in. And ngraphs is how we visualize it. So over the past 2.5 years, I've collected a lot of screenshots of interesting ngraphs that I've seen. And I decided to go ahead and start an internal blog where I could sort of explore some of the stories, the interesting stories that ngraphs tell, some of the lessons that can be learned from them, that sort of thing. As for why it's called ngraphs, well, there's sort of an unspoken internal rule that everything has to either begin or end with the word in. So anyhow, so what sorts of things do I post? This is one of the posts that I figured I'd start with because the first question I usually get when I tell people I work for LinkedIn is, why do you guys send me so many damn emails? Last July, one of my product guys actually posted on our Eng blog about how we've been actively trying to decrease the number of the volume of email that we send. So this graph actually shows about a year's worth of data. The green is current week. The sort of purple color there is previous week. And the reason I think, and you can obviously see this decrease over time, like right here is right around the July timeframe when Atif posted. The reason I like this, so this isn't actually a graph of volume. This is a graph of a deduplication cache that we use in order to deduplicate our emails. It has 1 item per email. And so you can sort of see that and a 7-day TTL, which is why the week over week sort of pushes out to the right. I just thought it was sort of an interesting way to look at it, not in terms of volume, but in terms of number of records in a cache that we use. I talk about interesting failure modes. This was really interesting to me because over there on the left, there was some database maintenance that happened. And after the database maintenance was complete, only one of the 24 machines running the service actually reconnected to the database. Just looked kind of cool. This, I talk about mistakes that we've made. So at LinkedIn, we'll canary new code to a single machine, and then if it looks good, we'll roll it out to the rest of the nodes. This was back in the bad old days before we had automation around detecting problems. So this is the canary throwing uncaught exceptions. And unfortunately, there was no automation around catching this, so it was like, canary it, go look at every graph of every metric that we have, and if none of them budge, then we're probably okay, right? The thing that drives me crazy about this one, this is the following week, where we kind of did the same thing, but it is what it is. I talk about interesting patterns that I see in ngraphs. The plateau is typically a pattern you don't want to see. This is actually a graph of number of seconds spent install time. So there's a natural plateau, or number of seconds per minute spent install time. So there's a natural plateau at 60 seconds, because that's how many seconds there are in a minute. Other plateaus, this is database hitting its explicitly set session limit. Other plateaus, timeouts, right? This particular service prefers to time out quickly rather than to continue to wait for a response. So as it approaches that threshold, you get this nice plateau. I call this one March of the Restarts. We have automation around being able to take action if thresholds are met. This is so the top graph is actually thread use for a particular service, and you can see each one of the restarts when it drops off. This is actually one of the upstreams of this service, and you can see the direct correlation between the latency of the service and when the restarts are actually happening. So I thought that was kind of cool. I posted a lot of unintentional art. This is actually a Kafka max lag graph, but I posted it because it looked kind of like a rainbow. This one reminded me of a Chinese dragon. I have no idea what this actually is. It just kind of looked cool. I've got young daughters. This reminded me of something they might draw. Again, no idea what it is. I post about external factors that can impact our site. So this is actually the Super Bowl in 2015. It's U.S. site traffic. You can see, you know, Idina Menzel kicks it off with the national anthem. Site traffic goes down. Everybody's watching the Super Bowl. Halftime starts. Everybody gets up from the couch and logs into their LinkedIn. You know, Left Shark takes the stage and everybody starts tweeting and leaves LinkedIn because they're so excited about Left Shark. You know, exciting fourth quarter rally by the Patriots, and then somewhere in here is where, you know, Russell Wilson throws an interception on the 1 yard line with 26 seconds left. Game ends and things kind of go back to normal. Yeah, threw this in there, just, you know, obligatory meme. Really, I put this in because the reason I do this is sort of as a cultural instrument for just getting people excited about their metrics and seeing how cool these things can be. Also, I would like it to not just be in graphs, so if you guys have interesting metrics that you have that you think I'd be interested in, please send them my way. That's my time. Thanks.
I'm the lead of the Intelligent Decision Systems team at Uber, and buckle your seatbelts because I'm going to give you a 360-degree view of observability at Uber. So first of all, why do we care about 4 nines of availability at Uber? Well, one thing is, in contrast to many other applications or websites, nobody comes to the Uber app to just browse. You never open the app and are like, oh yeah, this is interesting, cars are going down the road, closing the app, going about with your day, right? Every time you open the app, you want to actually take a trip, you want to give a trip, or you want to move goods around, right? And so this is why we want to make transportation as reliable as running water. We want to have our riders be so confident about the Uber app that they can open the app and be sure that they get to the airport on time, get to the doctor's appointment on time, for example, get to a meeting, an interview, a date, etc. Similarly, the riders that use our platform, they are dependent on us because every trip they're taking on the Uber platform earns them money. And potentially their sole source of income is actually driving on Uber. And so now it makes sense why we want to have 4 nines of availability. So as you know, 4 nines of availability means we can just be down for just over 1 minute per week. And so that means we need sub-minute alerting and mitigation, or alternatively, we have to reduce the end-user impact if we have any outages that are going on. And today I'm going to talk predominantly about the first part, sub-minute alerting and mitigation. So one thing is, obviously, we're a mobile app, so we have to make sure we monitor edge availability. The second thing is we do black box testing. Thirdly, we also do white box monitoring. This is actually a quite formidable task because at Uber, we have a staggering 500 million time series that we ingest. So that means we need to build a database that can write 2 million writes per second, and that can read about 1,000 reads per second. So we tested various different open source databases, but we found we had to build our own in-house database, which is called M3, that can withstand all of this load. We also built an in-house alert configuration and UI query language. Apologies for the missing graph. So basically, it should show you the UI that we have and the very neat query language. Here it comes. And secondly, we also want, besides the database and the query language and the UI that people can set up alerts, we want something that is more intelligent. Because 500 million metrics, suppose you only want to onboard about 1% of them to alerting. Who's going to set up 5 million alerts? And who's going to maintain these alerts with a 25% month-over-month growth at Uber, right? Nobody's going to do that. Furthermore, we have basically a lot of business metrics that look like this. They have a 24-hour cadence and a 7-day cadence. So basically, setting up static alert thresholds doesn't make a lot of sense. Either you're way too sensitive and you get woken up every Friday or Saturday night, or every rush hour in the morning, or you might not be woken up at all, and things are completely on fire by the time you get an alert. So this is where intelligent monitoring comes into play. We wanted to build something that had absolutely zero config. Nobody needed to know about any parameters they had to tune. It can dynamically adjust to any underlying growth, to any seasonality within the time series. And that obviously has the impact of greatly reducing noise and increasing the signal-to-noise ratio. So why is this a hard problem? Well, most of the outlier detectors for time series that are out there are static in nature. You have the luxury of having a lot of computation complexity can you use, and a lot of the data is actually not is finite in nature. This is very different for streams. You have an infinite stream, you have to make some trade-off what kind of data points you want to include, and furthermore, you have to do your computation fast enough before the next data point comes in. And as I said, this is within sub-minute kind of determination. So here's a list of requirements that a real-time monitoring system should have. And we actually built a system that satisfies all of these things. And here's the output of this monitoring system. So in the top red, now purple, and bottom yellow, barely visible, you can see the upper and lower thresholds this outputs. And then in blue, I added actually the after the fact time series values that we observed. So you can see we really nicely match the patterns of the underlying time series without having any prior knowledge of where it will go. And so this means that we greatly reduce the noise and we're super sensitive to any issues that might be occurring, even if the metric is increasing in volume over time. And another thing is that static thresholds cannot capture is that the maximum lower threshold actually can exceed the minimum upper threshold just a couple of hours after the fact. And this works, this system. So here's an example of a real outage that we encountered. The red point is where we actually found the issue. And you can see how quickly we could revert the offending deploy to get this metric back on track. But alerting is not enough. So one thing is to get an alert and to know that something is wrong. But the other thing is that you actually have to go in and you mitigate or roll back the change or fail over the data center. And in order to find this, you have to find out what the culprit is. Well, at Uber, we have about 1,000 microservices that all can potentially talk to one another. So it's really hard to disentangle that just by alerting itself. So what we actually did is we built a similar system to Zipkin-style tracing. It's actually open source. It's called Open Tracing API. And that allows us to actually do root cause analysis on top of this, in addition to ingesting event markers. So basically, what is going on in the Uber system at this given point in time. And if you're interested in learning a little bit more about this, besides a 5-minute talk, please come and see our recent blog post that we've posted. It has various different talks on various different topics on this matter. And with this, I would like to thank you for your attention, tell you that we have a booth here, number 16. Please come by if you're interested in learning more. Also, we're hiring. Thanks.
All right, so my name is Brian Martin. I'm a SRE at Twitter working on the cache team. And today we're going to talk about measuring high-performance systems, specifically using a tool called RPC Perf. So before I get started, some vocabulary. We're going to be talking about RPS, which is requests per second, a measure of throughput. We're going to talk about latency, which is time delay from request to response. And we're going to be talking about percentile latencies. So you'll see notation like P39, which is the 99.9th percentile. This means that 0.1% of requests are slower than this. Again, that's single requests. If you have fan out, you might actually hit this more often. So some benchmarking pitfalls. Fire and forget benchmarking doesn't give you as much information as active benchmarking. Like, you need to pay attention to both your load generator side as well as your client side, and pay attention to a lot of systems metrics. So be sure to apply Brendan Gregg's used method when you're benchmarking. Bad math, don't average percentiles. Don't do it. You don't wind up with real numbers when you do that. And broken tools, like a lot of benchmark tools are broken or they don't measure what you think they measure. So really question any results you get and dig in and learn your tools. So since I work on the cache team, this is specifically about cache. By cache, I mean in-memory storage within the data center. Typically used to protect your database from a bunch of queries. So Memcache, Redis, and the recently open-sourced Pelican cache are examples. It's a very high throughput service. We're talking about 100,000 requests per second per core. And low latency is critical. Oftentimes your customers expect that your P39 is maybe, 5 milliseconds or less. So why do we measure performance? We need to understand our system limits. We need to be able to plan for capacity And we want to be able to test for regressions and qualify new hardware and like infrastructure changes. It's not static. So you need to make sure that you're not messing stuff up as you move forward. So why a new tool? So the existing tools were pretty limited. They didn't have kind of the features that we were looking for. And a lot of them were actually giving bogus results. Like if you turned down the rate limit on something, the latencies were actually increasing. And this was due to a bad event loop within the benchmark tool. So wrote a new tool, and the requirements were that we would have high resolution latency measurements. We'd be able to produce trace files for further analysis. Wanted it to be reasonably efficient. Like, I don't want to have to use 100 instances to benchmark a single cache. And I didn't want any GC pauses, because that can cause coordinated emission. And additionally, we wanted pluggable protocol support. So Memcache, Redis, Thrift protocol, wanted it to be extensible and able to be used for other types of RPC services. So introducing RPC Perf. It's written in Rust. I'm using async networking through the Metal.io library. It does multi-workload support, so you can do mixes of gets and sets. And it's open source on Twitter's GitHub. So general usage, you can use it to discover your throughput limits. So you do that by running without a rate limit. You can use it to measure latency. So you would set a rate limit and see how the server responds at that rate. And it has a file-first configuration. So all workload parameters are through a toml config file, which looks something like this. Here you can see that basically we're firing off gets on random keys at a rate of 120,000 per second. And you get an output that looks something like this. You can see basically that we did achieve our 120,000 requests per second. And these are the latency statistics that we get at the end. So the most important one for me is the percentiles, specifically P3 and 4.9. So kinds of tests that you can do with a tool like this, basically you can do what I call vertical scaling tests, and this is basically how many instances can I run on a single machine while holding to our latency SLA. So find the limit for one, launch more, keep ramping it up, and then you can wind up with a graph that looks something like this, where you can basically see that the aggregate throughput on the machine starts to taper off as you saturate. Another type of test that you would want to do is latency versus throughput. So basically you fix the number of instances that you're running, and you ramp the rate up and see how things are responding, and this will basically show if you have some latency guarantee. This will show you the throughput at which you start to tip over. And you get something like this. So basically you can see as throughput goes up, the latency increases exponentially. And then, oh, that does not look good on here. Okay, so this is a waterfall style heat map. If any of you are familiar with Brennan Gregg's heat map visualization, this is that, but in the other direction. So we have time moving downward and higher latencies on the right-hand side of the graph. And this was on my laptop running between two VMs, so we actually get some kind of interesting data here. And you can see the 50th percentile, the 90th percentile, and the 99th plus is kind of a bunch of noise over on the right. So you can see that like this is not a simple distribution. It's obviously very multimodal. So regular statistics don't really work very well for this kind of stuff, but interesting to visualize and kind of see. So how has this tool helped? We have a much better understanding of our service limits now. We have a lot more confidence when we're qualifying hardware and making changes to our systems and new kernels, new network switches, all that kind of stuff. And we used it to test our new cache software, which is called Pelican. And that's it. You can find RPC Perf and the Pelican cache software on Twitter's GitHub page. And yeah, contributions and bug reports and stuff like that are welcome. Thanks.
Okay. I'm going to talk about engineering management, and I'm talking regarding feedback. Feedback equals results less expectations. Okay, I'm from Brazil, so sorry about some mistakes in language and stuff like that. Okay, I'm going to start with an example. Let's start with expectations. Probably most of you guys are expecting a top shot from a famous company. Then, the result, you guys got to see me, an ordinary man from an almost no company in Brazil. Well, in Brazil, we are kind of no, because we do some SaaS ERP online for small and medium business company over there called Conta Azul. The feedback is, sorry to disappoint some of you guys. Well, actually, feedback is kind of a math problem. If the results you come are equal or higher than your expectations, the feedback probably are going to be positive. Else, if your results are lower than expectations, your feedbacks are going to be negative. Very simple. Why? At the core, everything has problems. People have it, companies have it. What are companies? If only one person, then company issues are equal the person issues. If more than two persons in a company, then you got a relations. If you got a relation, you start getting relationship issues. So what is the point? If the feedback, if you don't give it after some fact or event occurs, this is pointless. Don't make it in a quarter or yearly review or something. Give the chance for the person that did it or committed a mistake to be aware of that. Let's start with the principle that people are good and are trying to do good things, and that are not doing things as a bad behavior or something like that. So don't wait that long to tell something's wrong. Give them the opportunity to change it, because probably they don't know they are doing something wrong. Okay? So try to give them that information quickly. It's like if you're in a relationship with your girlfriend or with your wife, then you don't wait to say that if she leaves the wet towel over the bed, it's a bad thing to wait like a quarter or a year to tell her that. You say that as soon as possible. Else you're going to be sleeping in a wet bed. So that's my quick talk about feedbacks. Don't wait that long. Don't wait for the yearly review, the quarterly review. Do it often. Do it as soon as it happens. Okay?
Hi, my name is Jeff Allen. I'm right now a dad at home in Osh, Kyrgyzstan, where my wife is working for Doctors Without Borders. I used to be working SRE a long time ago, and then embedded systems developer in Cisco, and now I'm ready to get back to being an SRE, into advertisement. I'm here to tell you a story. As SREs, it's our job to investigate problems, learn whatever we have to learn in the moment, and then get it solved. And then later, maybe we can talk to our colleagues. We should definitely talk to our colleagues and spread that information around so that they'll be more efficient the next time. I used to work with a guy named Arnold De Leon, who did an excellent job of this. He was always just telling us little stories, and every once in a while in a staff meeting, he'd tell us what was happening in the week past, something he got curious about, something he investigated. Sometimes he had a point. Sometimes he was really trying to teach us a lesson. Sometimes he had a mystery and he just wanted feedback. Sometimes he was just kind of giving us information and hoping that we would integrate it into our work going forward as we saw fit. So I'm going to do the same thing. I'm going to tell you a story, and I hope that in the next year you guys face something like this, and my story will save you some time. So it started off innocently enough. I just wanted a certificate. Let's Encrypt had general availability. I thought, woo, all right, cool. We're going to play with a new toy, get secure. So I thought, well, I'll use the Lego client because it's written in Go, and I love Go. And of course, I can't just use Go like a normal person. I'm on tip all the time because I'm like a Go, Go lover. So I, at that point, had Go 1.6 beta 1, and I just thought, oh, that'll be fine. Whoops. Oh, no. There. Whoops. Can't get my certificate, weird error, start debugging a little bit, differential diagnosis, compile with 1.5, and everything's fixed. Okay, but I'm not the kind of guy that leaves that, right? So I start digging, like, whoa, why is Go 1.6 breaking stuffing? That is totally not allowed. We do not allow that in the Go world. And so I did a bunch of git bisects, and I found out that the problem showed up in tip, what would become Go 1.6, when HTTP 2.0, HTTP 2 was turned on as the default in Go. What? Like, I hadn't been paying attention. I was like busy making sandwiches for my kids or whatever. What's this HTTP 2 stuff? Like, I thought they were still talking about that. Like, you know, okay, maybe I heard that like it's coming soon to Chrome or something, but why am I using it on the command line? I'm just minding my own business here, trying to get a certificate from Let's Encrypt. Why are they using it? Like, why is my client using it? It takes two to tango, right? I mean, how did their server get upgraded? Like, I felt shocked and surprised that I found myself in the middle of debugging HTTP 2. I wasn't expecting that when I was just trying to get a certificate. And of course, you know, why is it breaking my stuff? This talk is not about something that's wrong with HTTP 2. This talk is about the fact that it's coming, and there's the minimum you need to know so that when you face it, you'll know what's going on. The problem that I was looking into is solved. Don't worry about it. It's gone. You don't have to worry about it. So here's the absolute minimum you need to know. It is a binary protocol. It is usually, almost always hidden inside of TLS. That's what that little star means. It can be unencrypted, but the vast majority of implementations only ever send it encrypted, so you're only really ever going to see it as, you know, inside of TLS, which means you won't see it. So you're going to have to use tools to read it and to debug it. You're going to have to use a client that will log all the frames it's sending, for example. Because it's only the client that can see inside of the TLS. Or you can do tricks with Wireshark to decrypt it. But at least its magic number is in ASCII, and there's a funny story why. These numbers, parentheses 1, is pointing to references at the end of my talk. That's what this is about. This whole talk is just about giving you a list of things to go read about more afterwards. So go read that one, it's a funny one. HTTP 2 does pipelining. There's lots of requests inside of one TCP connection. That is where the biggest benefit comes from. But it means that if you're using HTTP on the command line, which lots of us do for SRE type jobs, or like batch loading jobs like that, you're going to find that you're going to miss out on some of the benefits of HTTP 2 if you've got a curl inside of a while loop. So you might need to rethink things that are set up that way. And also, this is a huge one. Go read this number 2, or it's a video. It's a pretty good video. It's also there's other resources linked to it. This says that things that we used to do aren't a good idea anymore. And it's not your job to fix them as SREs. It's your job to go find the web dev and say, hey, watch this with me. Let's make a plan for how you're going to stop doing this stuff that is breaking HTTP 2. The biggest one is domain sharding. Don't do that anymore. So you might be surprised how you end up talking to your first HTTP server. I was, for sure. So one way that it can happen is by using a CDN. So Cloudflare is very clear, and they trumpeted it really loudly, like, yay, we do HTTP 2 now. That's how I kind of first learned about it. But Akamai, for certain customers, I think it's opt-in. The customers have to say, yeah, we want you to do that. No, it's automatic? It's automatic or opt-in? Okay, so Akamai customers can opt in to having HTTP 2 front for their 1.1 origin servers. Another way you might find it is if one of your colleagues deploys a new microservice that's used gRPC. I haven't heard anybody talk about it, so I don't know. I guess it's not coming so much. So you need, so a good way to find out if you're getting HTTP 2 negotiated inside of your TLS session is H2I. You can go see where to find it. If you're using Go and you want to do differential diagnosis, you can turn it off, but don't run it in production like that. Or like Brad Fitzpatrick, who worked really hard on implementing this, will have my head. So don't use this except for diagnosis, but then do use it, find the problem, and let's get it fixed. Because it works great, but there's a million little edge cases we all just have to get through. The particular edge case I was dealing with was posts without content type, but only when passing through Akamai. If you're a bash user, you're going to have to recompile your curl because the most recent versions of everything doesn't have it, as far as I can tell. I guess no, Arch Linux, they always have it. But, if you're a Python guy, there's good news and bad news. The good news is you won't be surprised. You're not going to accidentally get HTTP2 because there don't seem to be any plans to put it into the Python core. There are or no? I'm right. OK, I got one right. As far as I can tell right now in the Python universe, you must opt in to getting HTTP2, and you do it by using this package Hyper. If you are using Java to do your HTTP client and you want to get the benefits of HTTP2, your best bet is OK HTTP. The reason why is in that reference, number 7, which is here. The reason why is because it's a more kind of beautiful API. It's an easier way to talk to things. Oh, I'm sorry, the URLs aren't there. You can take that picture if you want, but it's not going to help you. So to get this, you can either contact me directly or maybe USENIX will be hosting it.
Yeah, actually, for people who are doing lightning talks, mail your talks to slides@usenix.org. Just slides@usenix.org, production,
OK. Cool. I'm sure I'm probably over, so any questions? There's no time for them anyway. Next.
Okay, hi everybody. My name is Mike Christian. I run site reliability at Salesforce. I'm going to give a talk about getting to what I call no nines. As a caveat, this talk is not about Salesforce. It's about our industry. You can Google anything on here. It's all been in the news and blogged about, and it's all public. So as an industry, we once had a thing called DR, which does not equal high availability. It's all about disasters, airplanes into buildings, catastrophic fires, earthquakes, things that probably will never happen to you. And so people put about that much effort into it, right? And everybody had a personal DR plan, and this is a quote from an architect I was working with. Retire to Bali. Okay. HA planning is something different. We assume failure. We go from there. So I had a partner tell me once, as I was talking to him about this kind of thing, we've never lost a data center. Wow, that's amazing. A week later, they lost a data center. No, we just lost the edge routers. Sorry, dude, your data center was down. So the truth is, even the best data centers do go down for all sorts of reasons, from HVAC failures to squirrels to partial nuclear meltdowns and everything in between. And so we have to plan for that. Couple real-life stories, fake fires. This is a previous company I was working at. Somebody was soldering in the corner of the data center. A little whiff of smoke comes off. Yeah, when that red light starts blaring up there, it means you're about to trigger a fire suppression system. That means you either need to hit the big red abort button or get out of the data center. Our guys didn't either. Fortunately, we don't use Halon anymore. So they survived. HVAC suppression. This was another instance where we actually had one HVAC failure on the roof. It just kind of got a little warm in one part of the data center, triggered a soft fire suppression system. What's the first thing that happens? Shut off all of the HVAC. All of it. Data centers get hot really quickly when you shut off the HVAC. We had people running in there powering off systems in 5-minute shifts with wet cloths over their face. Ugly. But we have these wonderful backup systems, right? But they don't always work. This was a company I had my personal website hosted on in Florida, and there's a hurricane that hit. Okay, well, that's what generators are for, right? That worked great for about 12 hours until they ran out of fuel. Problem is they couldn't get new fuel for a week because it was a disaster area. Even some of the new technologies, people are doing flywheel UPS now. We saw an incident a couple years ago in the 365 main data center in San Francisco where there were periodic brownouts and it slowed the flywheels down to the point where they didn't have enough energy that when the power finally dropped, the UPS didn't work. It's now affectionately called 364 main because it was down for a day. Sometimes incidents can encompass entire metros, not just the data center. This wasn't a hurricane. This was a thunderstorm on the East Coast. So it took out multiple data centers, took out Google, took out Microsoft, took out AWS. All of these companies fell off the internet due to a thunderstorm. And of course, we had the unthinkable. I think everybody remembers Fukushima Daiichi, terrible earthquake, tsunami, thousands of people died. Partial nuclear meltdown, I never thought I'd have to deal with that at work. But rolling blackouts, you know, we had our data center kind of on thin ice. And these are kind of the big disasters you think will never happen, and certainly will never happen again. Except 2 years later, a rat chewed through a power cable, and Fukushima Daiichi lost all of its cooling to the reactor pools. And same thing happened. So typically, our industry addresses that with ops superheroes, right? We need more nines from our SAN, so what we're going to do is we're going to buy another SAN, and then we're going to put an OSS cluster software on top of it, and basically triple the number of failure points that we have, right? So I want to introduce you to Tainter's Law. Joseph Tainter studied, in this case, Roman mythology, not mythology, but history, and kind of explored the fall of the Roman Empire, and he came to the conclusion that as societies, we get more and more and more complex, it eventually leads to the downfall of these great societies. And I believe the same is true for technology. So what? So as our platforms grow, scale, and evolve, they get more and more complex over time to the point where they're almost organic and we don't really understand them. The more redundancy we put into there, the more complexity we're putting into there, right? And at some point, we have so many layers of complexity that we don't understand how anything works, and we're actually decreasing reliability. So what does that mean? So at massive scale, I think we all know this in the room, we cannot build reliable systems, but we can embrace failure and design around it. And instead of focusing on reliable systems, we need to build resilient systems. And the simplest way to do that is to focus across global regions. At a properly designed global architecture, as long as you have one region up and serving your users, you're 100% availability. So what if we just solve cross-regional failover really, really, really well? And just focus on that. Don't focus on your HVAC. Don't focus on your second SAN. Just focus on getting your users to a different region. If we did that, we can design resilient applications that depend on ephemeral servers, that depend on ephemeral data centers, right? Because you can build an ephemeral data center at half the cost with no HVAC, no UPS, no generators, and you could still get to no nines. Just 5 zeros, and as somebody pointed out, you want a 1 in there as well. Thank you.
Good afternoon, everybody. Unfortunately, I don't have any slides, but I'll try to explain one of my concepts which might be very helpful for the SRE world. Again, my name is Ramesh Nadimpalli. I'm a site reliability engineer at eBay. Today, I'm going to talk about an intelligent manager for web applications, kind of software SRE or a web application doctor, which makes applications resilient to problems or failures and take corrective actions automatically. When we talk about a web application, let's take a typical web application which contains thousands of nodes. And when I say thousands of nodes, each of the nodes can be typically a web servers, load balancer webs, application servers, and some other application servers nodes, and databases, and external services. Each of these, let's see what happens when they receive a URL request. When they receive a URL request, it goes through several nodes, either the load balancers, web servers, application servers, all the way to the database. And in this process, it uses resources from the host, whether it is the resources from the OS or the application server or the JVM and the database and external services, and any number of failures can happen here. Whether it is contention, whether it is deadlocks, whether it is high CPU, memory, and number of things can fail. And we exactly know if we categorize each of these failures, we exactly know what each of these failures what kind of trace it leaves in the logs. By analyzing those traces or the anomalies, we can map it back to the problem, failure, or problem or the failure. And the way, the crux of my concept is we have failures, we can categorize them. Each failure leaves some trace of anomalies with respect to the traffic, with respect to the errors, with respect to the response times. And these errors or the response times might cascade. The problem may be only with a few nodes, but it may impact several nodes. The design I'm proposing is the intelligent manager, where it has agents across, residing across every node, which actively detects the anomalies with respect to the traffic, spike or dip, response times increase or decrease, errors, whether it is system errors, data errors, network errors, etc., wide variety of errors. It tracks these errors, creates an anomaly record, and pass it on to the intelligent manager, where it analyzes all these anomalies, map it back to the original problem, but now we now know what the problem is, but we haven't identified where the problem is. In order to find where the problem is, the intelligent manager has to exactly know where each node stands, how they are connected, what is upstream, what is downstream. And in a typical scenario, say there are 20 or 30 nodes that failed, and it gave some anomaly records. All these web architecture, we have a tree-like structure, and based on where the nodes are placed, we can find the root and the leaf to find out the problem and the impacted nodes. Also the intelligent application needs to be aware of what are the changes being to the infrastructure, whether it is any new build going on, anything, etc. And once it knows the problem and where the problem is, the intelligent manager can take corrective actions, whether it is nuking, whether it is removing it from the load balancer, or redirecting the traffic to a different colo or a different load balancer, etc. I know this is a concept that it's very difficult without any diagrams. I hope these kind of ideas might help SRE to reduce their amount of work by over 80%. Thank you very much.